delta T is small. If you do a shallow quench, then the droplet that you need to make must be much bigger. Droplet that will survive has to be bigger. If you don't make a bigger droplet for deep quench, it's not going to happen. So, if you want to make, this is very profound information in terms of biomolecular condensates, right. If you want to make droplets, then the key variable is this quantity, how much quantity, which in turn is related to all this chi c minus chi c, molecular weight, all those things we talked about, all those prefactors come into play. If the quantity is large, then you can nucleate them, because the size that you need to make is small, therefore, you can keep on going. Okay. It is kind of counterintuitive, right, because higher temperature you will be able to make it easy. No, it is the other way around. Right. Okay. So, calculate the free energy barrier for this. I take this value, substitute back in here. So, the F star in kT, I do not know, that is 16 pi by 3 sigma cubed delta G square. I am pretty sure that is what it is, because I know that it is related to the volume, right. You can do the arithmetics, right. Put this back, take this, put this back there. Okay. It's some number like that. But again, the important thing is 1 over delta T square. So, if the quantity is small, not only you have to make a bigger droplet, but the barrier is also very large. When delta T is small, the nucleation barrier goes to the sky. Right. So, in order to make these droplets, you need to have delta T reasonably not small. It should be reasonable, not too small. So, in measurements, you need to, or if you want to do simulations, so you should not just do arbitrarily. You should design your simulation in such a way you go to that delta T is large enough. Then you will see, otherwise you will be waiting in your computer for a long time. You can go home to some place and come back. Right.
So, that means your delta chi can be small, right?
Say that again.
The delta chi, I mean, whatever chi you are changing, if the inverse relation, if I can.
Yeah, yeah.
Which means just with slight modifications, like post-translational modifications, you can tune all this stuff.
Probably, and that is why we get diseases. The post-translational modification kills us.
They are not very big changes.
No, it is very delicate, quite delicate, very quite delicate. Delicate it is, life is delicate. Yeah. Yes, but still we are resilient. Yeah, we can do it. All right. Okay. So, I think that this is a good place to stop. Right. Then it grows. Once you pay a price to cross a barrier, and then you make a stable nucleus, which will grow. Right. And you could, for the growth, you could write all the fancy mathematical techniques, like a Fokker-Planck representation and various things, in nonlinear, Boltzmann equation. So many techniques are available to look at the growth kinetics. Okay. But in summary, I must say, this is where again Lifshitz comes in, Landau and Lifshitz comes in. The growth dr by dt, in the early stage, after the viable nuclei are born, in the early stage it goes like square root of t. Okay. And a little later, dr by the late stage, it is a early first nucleation. And then in the growth, there are two possibilities. So, the early stage of growth stage, it goes to square root of t. Basically, it is a diffusion like. And then much later, they are collaborating. Then dr by dt. I should not have written like this. Excuse me. I should have written r of t. Growth grows like this. Sorry. Excuse me. R of t goes like t to the 1/3. Okay. The very early stage of growth, r goes to the square root of t, and that should not be surprising to you, because we talked about this Einstein's law. This means r square. It is more like a diffusion. R square goes like t, and that I think the theory has that signature of the Einstein's diffusion. That's how this happens. But at a later stage, there are cooperativity, collaboration, then you get t to the 1/3. That is like our Lifshitz slides on. The late stage of nucleation growth and late stage of spinor decomposition follow the same law. Okay. So, I am basically done, right. We started in a humble way from here, right? And we predicted phase diagrams. We looked at how to make measurements, how to interpret the parameters, and how to design them. We did that. And then we brought structure of this polymer chains into picture, and then we looked at the implications of that, and then using all these things that we have mustered, tied them together, we are able to look at the time evolution of these structures. Right. One thing I did not point out here is, in the last lecture I told you, if you have charged system, even in equilibrium, we have spontaneous selection of structure, micro phase separation, we talked about it. In a similar way, when you look at the kinetics, what happens is you have a cutoff of a wave vectors, where instead of looking at in the case of simple system macro phase separation, all wavelengths below all wavelengths larger than a certain value will grow. The large wavelength fluctuation would not grow, short wavelength fluctuation would not grow, only the wavelengths corresponding to the microphase separated structures, only they will grow with the time, and they get locked into that structure forever. And that's the thing, and that's, we can do this at another time, maybe next year. Yeah. Okay, with that I'm done. Please ask me questions if you have any.
I have just one stupid question. So generally this is an example of a phase transition, right? So phase transition, a classical system of this, not quantum phase transition, this falls under the Ginsburg phase transition, where symmetry breaks, right? So in this case, what is the symmetry analogy which is breaking there, and we can construct? So in the language of symmetry, degree of freedom will be doubling in this phase, right? And the way what you learned today is that you start from there and just evolve the system, you can study. But in a quantum condensed matter system, if you want to come back, because symmetry is broken, degree of freedom has increased, so we have to develop all this RPA and everything. It will take a matrix of structures. So what is the difference here?
Well,
you are capturing everything.
Yeah, this is good. Let's say the nice thing about these systems is the translational symmetry, translational degree of freedom, that symmetry is not broken, right? So whenever the order parameter undergoes a discontinuous change, that's the symmetry we are talking about. It's a symmetry. The order parameter could be plus and minus, right? When that is broken, we say classical phase transitions. In that context, that's the way we do it. So the order parameter, the sign of the order parameter has, that's a symmetry.
That symmetry is broken.
That symmetry is broken. Yeah. This is also true with the van der Waals gases, also true biocondensate, and all of them. But I think, please, the question is a very important question, right? The question is, the description that I have given is universal for all first order phase transitions. Birth of the universe, we write same expressions. I'm sure you do all. Birth of the universe. How is the universe born? We write this way. Baby universe is born, and if she is healthy enough, she will grow. And then there will be structures inside, depending on what else is happening. How is star born, and on and on. And how is a biocondensate born, right? So this is very universal. It's the basic stuff, and it's a responsibility of any physical or physical scientist to know this stuff. Cold.
So which book? You have two books, right? First book, and which one?
For these things, probably the second one.
Second one, the latest one.
Yeah.
Which?
Right. Any comments, questions?
I have one question that you mentioned about overlapping concentration, right? So can
So
we
I'll
say
meet you
that
tomorrow.
I'll meet you tomorrow. Yeah, no escape from me for 2 more days. Thanks to you, and thanks to you. Sorry, keep going.
So in overlapping if it causes the overlapping concentration, then the phase separation can happen, or it's not related to phase separation?
It's not related. It's not related. Yeah. Purushottam, questions, comments?
No, I'm just wondering that it didn't strike me before that we talk about universality in second order transition. And the universal is very well defined, and you can talk about it from RG concept. But it's the first order transition, and that again on kinetics. So I was just wondering, and I was thinking that it didn't strike me before. I mean, of course, you get that it will be 1/3 at late times and all this, but yeah,
Yeah,
very interesting.
it's universal. Yeah, I know. It's
But
very-
is there any, just like the one that in the second order transition, that universality, here is it that well defined?
Same thing, because well, this point is second order phase transition, as you know. The critical point, it's a critical point. Yeah, that's except that point, everything else is first order phase transition. As soon as you go down, first order phase transition, even infinitesimally away. And then you have all the consequences, everything that we talked about.
But I think that you carefully chose also you called it TS and you never called it TC.
First order composition, yeah. Not in the books though, but that I do.
Yeah, I mean people.
I know they are very sloppy.
It's very sloppy.
Very
and it's
sloppy.
Very different, and one should be extremely careful
Yeah.
with defining critical points.
Yeah, that's a critical point. For the audience here, critical point is second order phase transition, because the order of the transition is defined in terms of which derivative gives a discontinuity. In the second order phase transition, the second derivative of free energy gives a discontinuity. In the first order, the first derivative like specific heat, volume, things like that. Okay. Yeah, any question? There was another hand. You have.
No, I was just wondering, it's a very nice question that, if you have the concentration very large, very high, and the chain length is long, then I will get a situation where there will be a lot of frustration. I'm in a kind of glassy kind of situation when I will not see this. So, that limit is not coming into the equation. So obviously you are not going to that limit. So that is the kind of understanding.
Well, not quite, right? Because remember the Onsager coefficient, that's the transport coefficient. That has interactions with all the neighbors and also diffusion, right? The collective diffusion, and that's where it will appear if you do it. But on the other hand, for polymeric systems, it's very easy to get into glassy state, right? And it takes very long time. In all these things, we are talking about annealed cases. That is, they are able to explore the whole phase space. The kinetics is taking place. It's still the system is ergodic. Yeah. If it's not ergodic, then that's their problem, future problem for those people.
So what is the minimal element that you need to add to these polymers to actually see the glassy behavior, or you can see it even here?
See, it depends upon whom you are talking to, right? To me, if the barrier for one conformation getting converted to another conformation is significantly higher than thermal energy, right? Then it will make a glass. Okay, and in workout the other way around, similar to this one, the exponential of that barrier for between two conformations, e to the that barrier divided by t, you can calculate the time, e to the that barrier by kT, that gives you time. If the time is age of the universe, it's a glass, right? It is not. It could happen even at room temperature. It could, in our labs, we see that in aqueous systems, room temperature, right? And it doesn't change. It doesn't. The system is frozen. Glassy water, aqueous polymeric system at room temperature, they are frozen because the barrier is too high. Because another thing about polymers is they can easily, because of conformation entropy, you arrest the conformation entropy, the barrier goes up. All right. So that is a very hand waving argument. Okay, what is the number, right? Are you willing to wait for a year and then say it flows, or wait for 10 years to flow? That's the answer.
So basically, you have to have an observation time scale.
You have to have an observation time scale. And then you define a quantity. That's the way they define glass transition time, fragility and everything, all those things. They give an observation time. If
Otherwise, there is no way to do it.
It has
to be practical.
Yeah. For that particular, from that perspective, in terms of English, we can say everything is a glass, because your observation time is a picosecond, so it's not a glass. You can say, but it's a glass in principle.
We see this in simulations.
But simulations are deadly. You have to be extremely careful. Simulations, right? We do simulations, right? So we know painfully, we know what not to do. Seriously, because it gets stuck. Okay. Yeah, please.
It's only a concern if you're in the
Say it again.
phase.
Say it again.
This barrier is only a concern if you're in the nucleation phase. If you're in the spinodal region, then you're not worried about this barrier, though, right?
Correct. So, okay, see people say for the spinodal decompression the barrier is negative, okay, because spontaneous there is no barrier, right, it is spontaneous. So, there is no, that is why I wanted to emphasize when I showed a graph like this, not for free energy, that was a rate of growth. It looks dangerously looking very similar, but this is for the free energy. For the nucleation there is a barrier. For spinodal decompression there is no barrier, spontaneous growth. Okay. But the spontaneous growth is such that rich gets richer at the cost of poor getting poorer in spinodal decomposition. In nucleation growth, it is not that the case. The nuclear growth is everything that is born is healthy. It's healthy means the right composition, but the size may be too small. Okay. And in that particular case, this Lifshitz Slice-Off, that is basically the cannibalization, that is the bigger droplet or eating up smaller droplets and getting bigger. That is how that 1/3 law comes about. And this also, in another words, is also called evaporation condensation mechanism. Some of them are condensing, others are evaporating, and that is the way people describe these things. That's another